Greetings. Let's say we have this statics problem with which it is good to use the method of joints. So what we have here is a problem where we have some truss, which means it's consisting of beams, and for the primitive case that we consider it now, to present the method of joints, we consider that there's like no bending happening with no deformation happening with the individual beams, where beams are these lines, these segments that make up the whole truss, which is the whole structure. And the point here is, the instruction is very effective, it turns out, in a static context. And what we have here is not only the truss, but also some information about it. Namely, this one is very simple. It's made of 3 equilateral triangles, which have only 60-degree angles inside, and all the sides are the equal length of all these 3 triangles. All of them, the 3 sides of each of them is always 10. Whatever units, that is meters, and this is degrees. This is degrees, that's stated, but this can be meters or whatever. And yes, when we talk about forces, let's say we talk about newtons, but also I can just leave out, just use numbers for simplicity. So the point here is that we have this truss structure, and if you want to take into account also direction forces, well, let's look at that. So yes, we have this truss, then there is this load of 7 newtons going down at this point. Basically, when I draw the free body diagram, which I'll translate this into a free body diagram in a second, I'll name all the vertices by letters, so that will be helpful. And then we have some support structures as well. So we have these supports, this support and this support. It's very common to have one 2-value support in 2D. We've got 3 2D, by the way. Some 2-value support and one value support. And by those value supports, we mean how many degrees of freedom it blocks. So a degree of freedom is, it can translate, that's 1 degree in one direction, another degree is translating in the perpendicular direction, another degree could be rotation, and so on. So we have 2 supports, and namely, these symbols denote something. So what I want to do first, before we even introduce the method of joints, I want to actually redraw this into a free body diagram. So to redraw this, I'll just take the basic shape of it. I'll keep the forces, and I want to find something called the global equilibrium. That will mean that we're not analyzing, which by the way, this point here is to analyze the forces inside all the beams. But if we don't want to do that yet now, we first want to find the forces that are external to it. And what are the external forces? They are the global equilibrium together. Or when we're looking for the global equilibrium or using the global equilibrium equations, we find reaction forces, but they're external. Those are the ones. For example, this one going from the outside, none of the beams has the 7 newtons, it's just from the outside. Just like these supports will also be forces from the outside. So that's what we're looking for now. We'll be using equilibrium equations for a rigid body for this. So this is not yet directly method of joints, this is preparation for it. So now I'm drawing a free body diagram. So first, I look at what forces are working on this from the outside, it's just the 7 newtons here. So I can just for simplicity use the number only. It will be clear from context if I'm talking about length or force. Let's say by length I always mean meters, by force I always mean newtons. And then, yes, these angles stay. I just draw the outer shape of the body. And then, let's say we have these support forces. So when we have this symbol, what it means is that it can roll to the side, but it cannot translate vertically. So it blocks the body, this whole truss, it blocks it from moving up and down. So there will be a force that blocks it from moving up and down, that means a vertical force. But there will be no horizontal force. So this symbol can be represented by a single force, a vertical force. So there is a vertical force that we're looking for because it's justified by this support symbol. And this support symbol means a 2-value support, looking at from translation in x and also in y. So there's going to be 2 forces, one in x and one in y. So this and this perhaps. Now, the direction has to be guessed, but let's say because we see this going down, we would guess the other ones to try to compensate for that, so they're going to go up. Let's guess it that way. And even what we're looking for here mainly is the magnitude of these forces. As far as the direction, we can adjust later. So we guess some direction and then we see how it goes. So I guess the direction, and here I know there's going to be 2 forces applied at this point. One vertically and one horizontally, that's what I did. As far as directions, I think they'll guess right, but they might be guessed wrong, we'll see. And so Now that we established what forces we look for, we can also call it some names. So A, and it might be useful to also draw the inner trusses, although we're now not analyzing yet necessarily. Well, we will use this diagram anyway, probably. So yes, it's good to draw also all the beams that we have inside. So the whole truss as it was. And so what we have here is, what we've mainly replaced are these supports by forces that they represent. That's what we've done in this redrawing. And so let's call the vertices some letters so we can orientate ourselves in the problem. So I'll go like this: A, B, C, D, and A. So I call them my letters, and now I can also call the forces that are at these points. So if this is a vertical force at A, an outer one, maybe because of the A, there could be confusion because you'll be looking for forces also inside the truss. It's the main point of method of joints. And that will be, for example, from A to B, there will be some force inside this truss. So because there will be a force called like AB, I will avoid it now, and I will just say that there's two supports. So let's say, or reaction forces caused by the support. So let's say this is R1Y, because the first reaction is this point, and the second reaction goes here. So this is the Y part of this one. So R1Y is this vertical one, and R1X is this reaction, but the horizontal part of it. And here is just I'll call this R2Y, because there's just this Y thing, no X reaction force. And so I've called these outer reaction forces. And now using equilibrium equation, I can solve for the value of R2Y, R1Y, R1X. So how do I do it? Well, we've established that all the sides are 10 meters, and this is equilateral. So here actually we'll have a distance of 5 if we take it till this point as a distance perpendicular to this line connecting this bottom side to the top vertex. And so, by the way, what I'm saying is because now we'll use equilibrium equations, as I said, to calculate for the value of R2Y. And how I'll do it? I can choose to take moments, the sum of moments at point A, at this point. When I take moments at the point through which some forces action lines go, so these forces will go through that point, even if we prolong them, or even if we go on their tips are directly touching the point at which we're taking the moment. Therefore, the moments of these two, which are unknown, can be neglected, and so that way we can actually get to the solution. Otherwise, you would have too many unknowns. So I do on purpose take the moment around this point to get rid of having to include in the equation these forces. Now, how do we take moment? Well, the sum of moments should be 0 because it's a static situation. That's the presumption, and so that helps us because now I can just add up the moments of the other forces, and I'm just talking about global equilibrium, the outer forces, not yet these ones inside the beam, just the ones outside, as I said. So what are those? We have 7 rotating it like this. If it's rotated clockwise, it's usually minus, and if it's rotated counterclockwise, it's usually plus. So that means we have 7 as a force, but minus, times the perpendicular distance to the point at which we're taking the moment, sum, we're taking it at A. So the distance from here is 10 plus another 5 to here. So it's 15, so times 15. So this is the moment part for this force. And to take down this one, well, this one rotates the other way, so it's not minus, it's plus, because it's counterclockwise. When it rotates it counterclockwise around the point at which we're taking the moment, it will be plus in this sum, in this addition of them. So R2Y multiplied by its distance. And so its distance is this whole two sides, perpendicular distance. And even the perpendicular distance is not even confusing for beginners now because it's directly the distance at the same time also because it goes along the axis basically. So it's how much? 2 sides. That's 2 times 10. And so, yes, that's equal to 0. And now I can solve for R2Y. So R2Y, I use this equation. So R2Y will be minus 105 over 105. We add this to the left side. So 70 plus 45, 105 over the 20 to get 1 R2Y. And so that is what? That is 10.5 over 2. So it's 5.25. Yes, it's in newtons by the way, but I'll just write it as numbers to save time. And we know, as I said, we've established forces are taken in newtons and distances in meters, let's say. Let's just leave it that way and we don't have to write the units all the time. So that's that. So we now have 5.25 is this R through Y. Now how we get the rest? Now we can just use the equilibrium equations for direction forces or the whole directions of forces. So I can take all forces in the Y direction. They have to equal to 0. And I'll take the ones going up are plus, the ones going down are minus. So what do I have? This one going down, and I'm just taking again external ones to get to the value of R1Y in this case. So it's minus 7 because of this one, then it's plus 5.25 because of that one that we got now, and then it's going to be plus R1Y. So what does R1Y have to be for this equation to be satisfied? Well, minus 7 plus 5.25 plus something is 0. It's 7 minus 5.25. Well, R1Y will be 1.75. So this will be 1.75. And then the same thing we'll do for X. So all X forces, their sum. So what do we have? Well, now it ends up letting us know that yes, R1Y is nothing. Actually, it won't be there. The reason is because there's no other horizontal forces with which we could calculate it, and so it just doesn't exist. There's nothing against it. No other horizontal force going in the opposite direction, or even in the same direction that we would guess the direction of. So R1Y is actually we can ignore. So now that we've established these values that we needed, we can start doing the method of joins directly. So method of joins will involve taking some point and then around it doing an equilibrium again. So the same thing that you were doing for this entire shape here, global equilibrium, we'll do it for a concrete one point. So how to do that? Well, I choose one point and start it there, and then I continue. So we'll see how that goes. As far as I can tell, it might be useful to start, for example, at this point or at this point, because if we start at some wrong point, we won't be able to continue. There are some points that we can at least determine some other beams, inner tension and or compression forces, inner force in that beam, so that we can continue to the next beam or to the next joint. So in some other joints, it wouldn't work. We would just get stuck. So let's say I choose for the beginning joint B. So if I choose that, then what I have is basically what I do for method of joints is I draw the joint and I draw all the beams around it as forces that go into it or go outside of it based on what we know already. Also the values I know I will put there, and then I'll try to solve for. So I'll see the joint as a free body, and these beams are just cut off like this. And that's an isolated thing, and that will be a static thing that I'll look for the values of these forces inside. So that's the point here. I take A. So let's say I start with the joint A. Basically doing one joint after another. That's the idea of this method. So doing one joint after another. R1Y, we know it goes up. That's determined. We don't have to guess it now, we know it because we calculated it from the external equilibrium. So on this joint, there's this external force, 1.75 from below. But we also know there is some other beams connected to it. And now, the general, this beam is at 60 degrees by the way. And that's important for the calculations. I won't evaluate trig functions by the way in this video. Just write the sine of 60 or something and leave it that way. But you can enumerate it if you want. The point here is that these two are at 60 because we just cut out this, and now we analyze it. And now we can analyze it in statics again as a static thing, and we can enter these values here, and it will work. So the point here is that this joint A, we know this force from below, and we don't know these two. When we don't know them, and we don't even know their direction, by the way, if they go away from the joint, they're called tension. and if they go to the joint, it's called compression. And then also, if at this point we see they go away from the joint, from the other side, from this joint, they will also go away from the joint. So like, if we look at a cut here, it will go like this. If we go then, and we determine it to really be that way, then we will already know that from this joint, they will go like this, against each other. So in any case, we have this 1.75 from below, and then we have the 60 degrees here. And so, what can we do with this? When we don't know the direction, the usual approach is to guess all the forces are tension forces. They all go away from the joint. So if you don't know the direction of the forces that are around the joint, going into the joint or away from the joint, you don't know which of these two it is, then say that it's away from the joint. And if some result is negative, it will mean that it's to the joint. So just the direction will get switched later. These two, because I don't know the direction, I will therefore say here go away from this joint. So this is the A value. I just call it away so that we have space for it. So now what do we do? Well, we know this is at 60 degrees, and we know this is 1.75. So I do equilibrium equations for this joint. So now when I'm talking about sum of fx, I'm talking about sum of fx only around A. As we draw it here, I'm no longer talking about the whole global equilibrium. So there's the thing, local equilibrium kind of, and the global equilibrium from the whole body for the external ones, or the internal. But yes, it's true that actually when we talk about the joints, we include even the external forces that we have calculated together with what we're looking for, namely the beam, the forces inside the beams. So let's do it. Well, let's say I do Fy now, because I don't know this force. By the way, I will call it somehow. That's A to B, so I'll call this force AB. So this force AB, I just mean the line segment, but I really mean like some force AB that I'm looking for. So AB, and let's say I take the magnitude of it, so yes. And so this force AB will, I just leave it. There's many ways one can write it or decide to use what kind of notation, so, but let's just go this way. So this AB goes like this at this angle, and then we have Fy. So if we do all things in the y direction, they must equal to 0. So we consider static equilibrium also for the individual joints. That's what helps us here. That's the whole point. How does that work? Well, we know 1.75 is going up, 100% of it. And then AB is going, well, we guessed it to go up, probably it will go down, but at worst it will just become a negative sign, and then I can switch the direction in the drawing, or leave it and leave it with a negative sign. In any case, AB is going like this, and is basically only going partially in y and also in x, so we can break it out into components. Y component of it and x component of it. And so if I'm talking about the global equilibrium in y, I have to just take the y component of AB. So what will that be? It will be AB times the angle in a sine. So if you take the y component, it's sine of the angle at AB. Here it's the 60 degrees, so sine times sine 60. So AB times sine 60 is the y component of AB. So now I can solve for AB. Therefore AB should equal minus 1.75 over sine of 60. And yes, as I said, I won't evaluate the sine values now, let's just leave it. Might get a little messy, but we'll leave it that way. And so now sine 60 is positive, and this is a negative thing. That means it shouldn't have a negative result, but it ended up so. And for that reason, what I can do is I can just write that AB is minus 1.75 over sine 60, and it will be a negative value. This, if it's gotten fully enumerated or approximated, the sine of 60 and put it as a single number, it will still be negative. That's why. That's because the sine of 60 is positive. Then I will write a negative value for AB with this direction. Or I can just say that no, the guess was wrong, and the direction is the opposite direction. It goes towards the joint A. And then I can say that this is plus. But also it's good to change it here, so to say minus. So the whole guess would be different, because now the y component could be opposing itself with the only other y thing in this joint, at this joint. Which makes sense, that's what we want. If we only see something horizontal and two forces opposite to each other, that's right. But if we saw two forces in the y direction and both are in the same direction, that's wrong. One direction of one of them is guessed wrong. And so, well, it can be even direction of both of them, but if we already figure out one and we know it's right, even with this direction, then the only other one that we're guessing is being guessed wrong. That's the point. So AB is this. And so, as its magnitude, we just adjusted for that. So now I can draw it into our whole diagram. We now know that there is this force that goes to the joint. So because it goes like this, it also gets in the opposite direction at the other joint. And its magnitude is 1.75 over sine of 60 degrees. Now, we can continue the same way with the next joint. But before we do so, we can already also determine the internal force in this one. And because, by the way, on both sides, on both joints at this beam, it goes towards the joints. It's called compression, and it's there's like a C put at the beam. So two informations have been found, and those are the ones that we need for every beam. It's called compression, so it's C here written as that, and then we also know the magnitude of the force in the beam, the strength, the tension inside the beam. So now we have that. Now we can also get AC from this same thing here. So I can use, and one has to get an intuition or get used to what he needs to start with and how to proceed to be efficient at finding quickly things using the method of choice. So to not get stuck, not to do Fx first because it might be easier to do Fy first. So the equivalent for x forces, 0 as always. And then what do we have? Well, we figure out AB to be this, but we know that that's the yes, we know AB what is this, but we now take care of the x component. This field called AC, by the way, I'll call this AC. So this force, I guess again, away from the joint as I always guess, and in this case it will be right because it goes to the right, and the only other thing involved in the x direction goes to the left, and we know it goes that way. So now it's guessed right, we know already. It will end up being positive of the result. So AC, what will it be? Well, AC goes to the right, so we write it like that. It's plus, and then to the minus, what goes to the left? So minus is AB goes to the left, but we only write its x component, which is cosine 60 times AB, minus cosine 60 times that AB. So AB times cosine 60. And now we just solve for AC. So AC therefore will be, now we can add it. So AC will be AB cosine 60 basically. And what is that? Well, AB is this. So we multiply by cosine 60, so it's going to be 1.75 over sine of 60 times cosine 60, and that will be arctangent basically. So we can say 1.75 times arctangent of 60 degrees. Okay, so we have that. And now we can continue further. We can continue with this idea and use it in the next joints. Now, it depends on what joint you want to use, but now most likely next to choose would be B. So we will now focus on the joint B, and we will continue this way. In this video I might not finish all the beam forces, and because it's already getting quite long. So let's just do B for now. So to do B, I'll write it probably, or maybe I'll write it like this. I'll write it on the left here. So let's say we're considering the joint B, separated like that. And what's at B? So we know AC will go towards B at an angle of 60, of course. So it's going to be 1.75. If we enumerate it, it will be probably nicer, but this is the most exact form. One can also do the root form with the roots and so on, but with the radicals, but let's just leave it this way. So 1.75 over sine of 60 degrees is AC, and it goes towards here. I guess all the AC anyway. no matter that we know it already. And then there's something, there's some other forces. So there's this beam and this beam. So again, I cut it like this. I know AC is going towards it and I know its direction and its magnitude from the previous calculation. Now also let's take care of these other two. And again, we don't know their direction yet. So let's guess they're away from the joint. So they're away from it, let's say. And now we can calculate. So by the way, we know this is 60 degrees and this is 60 degrees. And so this imaginary thing is also 60 degrees, by the way. So that's what helps us. All the degrees, all the angles are same in this truss. That helps a lot and saves a lot of time. Okay, so now that we've established this next joint, I'm only talking with this magnitude about AC, by the way, just to remind it. And now let's take into account some information. Equilibrium at X. This is a little trickier because we actually have two unknowns in this equation, and that's not very nice. So we might actually try to do Fy. So y, what will it give? Well, it will be cosine times AC, and the only thing that will go against it will be the well, it will be the sine of AC. The only thing that will go against it will be sine of BC. So it will be sine of and BC is probably guessed right here. So sine of AC, sine of well, sine of the angle at AC times AC. So sine of 60. Because I'm taking this angle. Times AC, which is 1.75. Over sine, so it will cancel out. This may be one advantage of the keeping all the three values unevaluated. You can simply cancel things out if they do cancel out. Although it will be also noticed with the numerical calculations, one will just see it anyway with accuracy to 3 decimal digits. One would see that it's again 175. Doesn't matter, and so these two will cancel out, and so this is the y value for AC. I know the value for AC and the y value for it, and then I will minus. The only other y thing is the y value of BC. Minus sine 60 of BC. So sine 60 of BC is the times BC. So the y value of BC equals the y value of AC in magnitude. So what we can do is actually cancel these things, and we see that BC directly equals to AC. So we can say here directly, we know that BC, the direction was guessed right because nothing went negative. So the direction should be like this, away from the joint, and here also away from the joint, therefore. And it should be 1.75 over sine 60. Now, this is a nice thing, and we can again continue to the next joint. So what we can do next is we can consider this joint and go further, but I'll just leave it here, and you can complete it yourself if you're able. Try it out with the idea we've presented here. Try to follow the pattern. The most important thing is to realize that you should choose the joints with the most known forces, with the biggest amount of forces from the surrounding bars that we know, and with the least unknown forces, and so that you can maximize your probability that you'll be able to use that joint to calculate as many new forces as you can, and move gradually to the neighboring joint. Don't just jump around too much unnecessarily. You can just go gradually, joint by joint, and eventually we will have solutions for all the joints. And one thing to remind also, when you don't know the direction of the force inside the beam, this is away from the joint. But what it will mean is that from the other joint, it will also go away from the joint. And if it ends up being to the joint, these are just guesses, so I will just remove them because they're not the truth. Here I'm already writing the truth that we found out. So maybe better to write it here. So if something goes into a joint, the joint on the other side of the beam will also go, the force will also go into the joint. And this is called compression.